Okay, we are in section 1.6. And I've listed here, I put the direct proof for all x p of x. So remember now, these are talking about existential quantifiers, existence and for all. So this is saying for every x, p of x has to be a true statement. So to prove that, you're going to let x be an arbitrary element. What does it mean to be arbitrary?
Any variable.
It's any variable. There's nothing special about it. It just has to live in the universe. So the universe you're going to assume has been named, so you know what you're talking about. Are you dealing with kitchen cupboards or plates or oak trees or whatever your universe is? Then you're going to work through your proof so you can conclude that p of x is true for the x that you chose up here. So if you said x equals to 4, is that arbitrary? No, that's a particular value. Showing something is true for a particular value only means that you proved it for that value. Now you have to go prove it for all the infinite other values in your set. And so here is why we do proofs, because you can show it once for an infinite number of things. And then a proof by contradiction for all x, you're going to negate for all x. When you negate for all x, it becomes there exists an x. So there exists an x so that p of x is false. What you're going to do is you're going to assume that t be an object so that p of x is false, and come down just like our proof by contradiction here. Q and not q is going to happen. Thus, there exists an x not p of x is false, and therefore conclude for all x p of x is true. So this looks just like contradiction right here, except you're negating the for all x p of x. What does it mean to negate for all x p of x? It simply means that it becomes there exists an x, not p of x. So that's your assumption. Assume there exists an x so that p of x is false. Then you're going to get q and not q. We don't know what that statement q is going to be, but it's going to be something. And then you're going to conclude that there exists an x, p of x, not p of x is false. Therefore, your original statement is true. And then there exists an x, p of x by contradiction. It's going to look very similar. You still have for all x, not p of x. You're negating there exists. When you negate there exists, it becomes for all. So you have, suppose for all x, p of x is false. Then you're going to come down, you'll get a q and a not q, which tells you that there exists an x, p of x is false. Therefore, there exists an x, p of x is true. So here again, it's your whole contradiction thing. You have your q and not q happening here. And the top is always negating where you're starting right here. So you negate where you're starting. That becomes your assumption. You have to show two things that are contradictory statements, and then you draw your conclusions. The last form of proof in this section is this exclamation point thingy. What did that mean? There exists a unique solution. So it means there exists a unique x so that p of x is true. You have two steps for that. You have to prove that there exists an x so that p of x is true. And then you have to prove that for any other y and z, if p of y and p of z are both true, then y equals to z. So there's two steps for existence and uniqueness. You have to show existence. You can use any of the methods we talked about. And then after you show existence, you have to show uniqueness. So you assume two of them satisfy the criteria and show that they have to be equal. And that gives you existence and uniqueness. Okay, so let's look at prove that for every natural number n, 4n squared minus 6.8n plus 2.88 is greater than 0. This is an existence. This is a for every proof. So how did we start our for every proof? And we're doing a direct proof on it. So let x be an arbitrary value in the universe. What is our x is our n in this one, and what's the universe? naturals. Okay, so let x be a natural number. Now, where are we trying to go? Yeah. 6.8 and plus 2.88. 6.69. So I don't know where to go from this and in the naturals. So I'm going to go to the end and work backwards. What do I know factors into 4n squared minus 2.8 and the 6.8 and plus 2.88? We can factor it. Maybe a 2n. I need both 2n minuses on both of them, right? I don't remember how that factors. 0.9 and 0.8? Okay, so we'll make this be the 0.9. Do what? Oh, and they take the 4 outside? Oh, that might make it easier. So if we have the 4 out, then what would it be? Four, 2, 28, 7, 2.7 plus 72, 7.2. Oh, 1.7. Boy, am I off. Oh, that one is right. Oh, this is 1.7. Yeah, there we go. Yeah.
1.7 and then 0.72.
There we go. Very good. And then go backwards then one more step. That's n 0.9 and 0.8, right? Now, why would I know that all of that is bigger than 0? Because that's what we're trying to show. Well, we know 4 is bigger than 0, right? And n minus 0.8 needs to be bigger than 0, and n minus 0.9 needs to be bigger than 0. Yeah, since n is a natural number, yeah, n has to be greater than or equal to 1. So we're going to have n minus 0.8 is bigger than 0, and n minus 0.9. Then multiply since the product of positive numbers is positive, okay? I need a 6. And then what's our conclusion? Every natural number. Oh, isn't that one? Wow. Hey, at least I didn't replace it all. I've done that before. Yeah, that's actually a function of LaTeX. I don't know why it's a function of LaTeX, but I've been told that it's a function of LaTeX. it has something to do with how it connects up to LaTeX. But I don't know how that happens. They keep saying that they're gonna fix it. They've been promising that for the last couple of years now. And I haven't seen the newest version yet, so. I mean, I haven't seen that fix yet. That's supposed to be in the newest version when they get it made. Okay, so our proof there is complete. This one for a direct proof. Do we need to do that one? Did you guys understand that if x is an even integer, x squared is even? We've been doing that for years, it seems like, well, at least weeks. But this one was actually more interesting. It says for all rational numbers x and y, x plus y over 2 is a rational number. So what would be the hypothesis for this one?
X and Y be rational.
Yeah. Oh, I don't have that on this one. Oh, maybe it's this one. Nope. I have it on my home computer. I have shortcuts on different places. Let x and y be in the rationals. We are trying to get at x plus y over 2. Is rational. There we go. So how do we get to x plus y over 2? First of all, what do we know about rational numbers? Yeah, they're fractions. I don't know, P, Q, R, and S in the integers, such that I guess we're going to make Q and S not equal to 0. And we're going to have X is equal to P over Q. And Y is equal to R over S. So we can come down here then and plug in for what x plus y over 2 is going to be, right? So we're going to have a fraction and a fraction. This is going to be P over Q plus R over S over 2. Well, let's get our common denominator. That would be Q and S, right? And so we would have PS plus QR over QS all over 2. What can we do with that 2?
Put it next to the QX.
Next to the QS. So we have PS plus QR all over 2 QS. But that's in the rationals, right? Because QS is not equal to 0. Now, all we have to do, that's all we have to do. I thought we had to show it was a midpoint, but we don't have to. It is a midpoint, so I know it's between x and 1, but that wasn't part of this proof. So we actually can take all of that away. And then our conclusions. Thus, for all rational numbers x and y, x plus y over 2 is a rational number. Notice when it's for all, you're just letting x and y be in your universe. That's your hypothesis for those statements. Or for all, it's going to be let x and y. Now the next one that they did was a proof by contradiction. Tell me about this one. Prove that for all x in the interval 0 to pi over 2, sine x plus cosine x is bigger than 1. We're going to proceed by contradiction. So contradiction is going to tell us if we're negating for all, it tells us what?
That there exists.
Uh-huh.
That equal.
And it, sine x plus cosine x has to be less than or equal to 1, right? Now, what do we do next? We're trying to arrive at a contradiction of some sort, anything.
I can remember what the book said.
Well, what do we know about sine and cosine?
They have to be positive on
They're
that.
positive on that interval. Oh, that's not what I wanted. They're both positive on that interval. So what does that tell you about the sum of these right here?
Also, have to be
It has to be positive. So less than or equal to yeah,
Fine.
like sin x, sine x plus cosine x less than or equal to 1. Didn't they square things about now? So then that tells you that 0 squared is going to be less than sine x plus cosine x squared is less than or equal to, oops, that didn't work. Less than or equal to 1, right?
I see for some of these proofs, and like, especially in the next one, it's hard for me to tell how somebody would just think, oh, it's just square. Just try square.
Well, we know that sine squared plus cosine squared equals 1.
So we could probably try that.
That would be why we'd square. Yeah, some of them was like, who would have thought to do that?
But wait, is that different from between sine square plus cosine square and one like this one?
Yeah, it's going to be different. We have to FOIL it, right? So you're going to have 0 is less than sine x. Well, I don't want to put, let me put the square right here. Sine squared x plus 2 sine x cosine x plus cosine squared x, right?
What's the shortcut for the exponent? Because I made like a.
Control H.
Oh, really? I made a
Yeah.
typing shortcut, and I always have to put backspace every time I do that. So Control H is
Control H is up.
Control it up and down.
Control L is down.
Control H. H means higher. L means lower.
Really, like,
I just
perfection on.
I just typed to the, so 3 to the backspace. Put the number. So not backspace, the back arrow.
Back arrow.
Yeah.
Yeah. So then tell me, what is sine squared plus cosine squared?
1.
Yeah, so we have 1 plus 2 sine x cosine x is less than or equal to 1. Now, what do you think we should do? Don't you have an itching desire to cancel your ones?
Sure.
Sure, so let's subtract 1 to everything. But didn't we say someplace that sine and cosine are positive? So what do we know about the product? Yes, this has to be greater than 0. which is a contradiction.
I mean, I feel like without canceling the ones, you could already see because
You-
one plus
plus
something has to be less than equal to one.
Yeah, which is impossible too. And so then you go back and fix it. Thus, for all x in that interval, we have some. And we're done. That makes sense? Now, this one is probably the simplest proof that you outlined, but it's the most difficult one to figure out.
Yeah, I would never.
That all they did is tried it, and they sort of explained how they tried it. It took them. Maybe I was reading that someplace else. Like,
No, that's true, but then with the fifth power, they had
Yeah.
to wait until like 1960 something when they had a computer to do it for them. But I mean, like, who's gonna sit around and be like, I bet you that there's a natural number of fourth power is the sum of three other fourth powers.
Not
Let me try all the
only
numbers
did they
till I
not
figure
have
it out.
computers, they did not have calculators.
I know. I'm just like, who has time for that and why? Like,
And not only that, but they died when they were like 40. So they have a half a lifetime to figure all that out.
why? That's such a waste of lifetime.
They just did a lot more with their brains.
Sit around trying to prove that the triangle really did work.
That's right.
Oh, like for the
Trying up the different sides. Is there a number that doesn't mess for this? Times 1 squared 2 squared.
I
Do
know.
you ever just not believe anything that someone really figured it out?
Well, yeah, but not with that.
not with the triangles.
Whatever you value, you have to figure out that's what they value. You have
It's-
different priorities.
It's not the property of numbers.
For them.
It's not the property.
Yeah, we understand that. Okay, so how did they do that? On the proof of this one, the only important part of this, and I'm not actually going to write the proof up, you are going to figure out ahead of time. I'll type every other word. Figure out ahead of time what works. And then just exhibit that it works. Don't show me how you figured it out. I don't want to see that.
Search that.
Yeah, don't tell me that part. Just tell me that it works and show me, tell me what you're going to show that it works, and then just plug it in and show that it works. Those are the hardest ones to figure out because you have so much work to do ahead of time. And then you have to show that that one value actually works. The next example, I'm actually going to just skip it because I want to get to the ones at the end. They're more fascinating. But if you're talking about something having a real zero, it all hinged on the fact that that's an odd power. That means you have 71 roots. Complex roots come in pairs. So you could have, one real and the rest could be complex. But it has to have at least one real to have an odd power. If it's even, it could be all complex roots. Mm-hmm.
So I think it's slightly discouraging that I've never even heard of the fundamental theorem of algebra or complex number theorem at all. So it's like
You took pre-calculus, though, didn't you?
in high school.
Oh, they might not have used that terminology. But you talked about finding the number of zeros for a polynomial.
Honestly, I don't know, and I don't remember. Like that's why I'm really bad
Oh.
at doing stuff like that.
It just comes from the highest power. So that would have up to 71 zeros. That would be where it crosses your x-axis. Could cross it 71 times. But it might only cross it once because that's an odd number, and the rest of them are complex numbers, which means it doesn't cross it, but those are complex numbers that will give it zero. Then you'll take a complex variables class before you're done, so that'll make more sense.
Yeah,
How'd you like the example about the hikers? How they proved it?
it was
It was
slightly
bad, though, I thought I would have put a sentence down.
Sorry about that. Yeah, the hikers, you just start a hiker from the bottom, a hiker from the top, and hiking towards each other. They have to meet someplace unless one fell off a
There's gonna
mountain.
be some advanced mathematical way to, I don't know.
I always, when I first saw that, I thought, fixed point theorems, but I don't have any derivatives here, so I can't do that. And yeah, there's some really nice fixed point theorems to show you where something has to remain the same, but you have to have functions for it.
But that someone has hiked the wrong way so that you can.
No, they're hiking in the right direction. We're not letting, there's only one way to go. And they start at the same time and they end at the same time. But they can't fall off. It's well fenced. They're on some sort of strap to keep them on task. Okay, this one right here, between any two rational numbers, x and y, where x is less than y, there's always another rational number, z. So this is an existence proof. We have to give a value z. Now, if you recall from reading, the book gave the midpoint. It doesn't have to be the midpoint. It can be any value between them, but the midpoint is probably an easy one to calculate. So that's what they use the midpoint. It doesn't have to be the midpoint. So let's look at what's our hypothesis going to be here?
Such that x is less than 1.
That x and y be rational numbers such that x is less than y. Now, they're going to choose z to be the midpoint of x and y. So that's just a value that we're going to be able to show is between them. What is the formula for the midpoint? Let z be equal to x plus y over 2. Now we have to show that z is a rational number, and we have to show that z is between x and y. How do I know that z is a rational number? We proved it about 4 theorems ago, right?
So 2 rational numbers.
Yeah, okay, we'll do that. Since the sum of 2 rational numbers. Z is rational. Now, how would I show that it's between x and y?
Cool.
X is equal to, we're adding two things together and dividing by 2. So I'm going to put x plus x over 2, right? But by our inequality, we assumed x was less than y. So I can say that's less than x plus y over 2, correct? By substitution. Now do our substitution again. That's going to be y plus y over 2. But what is that equal to? Y. I have one inequality here, and this is my value for z. Right there. That x plus y over 2 is z, but that's less than y plus y over 2. Yeah. Oh. And so, I'm in the wrong spot. This is less than z, is less than y. Draw our conclusions. Between any two rational numbers, there's always another rational number. Now, I'd like to take this opportunity to point something out to you. Between any two rational numbers, there is an irrational number. Take any two rational numbers, find where they differ in the decimal point, and change it to something in between both of those. As you go out, now you change it at one point, and then you just keep it on extending it. Don't let it stop, and it'll be between. So you have between any two rational numbers, there's an irrational number. Between any two irrational numbers, there's a rational number. Yeah, you can terminate them. Now, which one do you think there are more of in our number system? There's by
More
far and above
irrational.
more irrational numbers. If you take the rational numbers out of your number system and you walk along your number line, you will not fall through your number line. If you remove the irrational numbers from the number system and walk along your number line, you'll fall through multiple times, infinite number of times. It's enough to blow your mind away. But it's a property of infinity. You never run out. But one is uncountable, that's irrationals, and the rationals are countable. As in, if you started counting, you have all of eternity and then more eternity and so on. You can
But why
count.
they make those numbers?
He's like,
There's infinite, but we call them countable because you can put them into a relationship with the natural numbers. So you can say, okay, that rational number is 1, that rational number is 2, that rational number is 3, and you can put them in that relationship.
wouldn't there be like an infinite amount of irrational numbers in between every or every integer? You know, be like between 1 and 2 that so like that's what it's like. So that's like a lot more.
It's a lot more, but between any two irrational numbers, you have a rational number.
Oh,
You
true.
don't ever have irrational numbers next to each other. There's always a rational number between them. In some places, there's just that many more.
There's, so there's rational and post rational and irrational is real number, right?
Do what? Say that again?
Rational and irrational and real number.
They're real numbers, yes.
So which means the real number and the irrational number would be the same amount, right?
Yes, real numbers and irrational numbers have the same amount of them.
No, it doesn't.
Imaginary numbers? Imaginary are going to be like the reals because you just take the real number and multiply by I. Yep. That's true. So that's always a fun little thing to ponder. Just about as good as Gabriel's horn in Calc 2. You guys remember some of you are still in Calc 2. We're going to get to Gabriel's horn. It's a surface of revolution. It has finite volume and infinite surface area.
Oh,
You can't paint it by the amount of paint that it can contain. Another thing of infinity. Yeah. Okay, these are the proofs that I wanted to get to. What? Gabriel's horn. As in the Archangel Gabriel? Yeah, Gabriel's horn. I don't know who named it that, but the name stuck. So it is cool. Okay, so prove that for every natural number n, there's a natural number capital M, such that for all natural numbers, got enough natural numbers? For all natural numbers m bigger than capital N, m, we have 1 over m is less than 1 over 3n.
Yeah, I was confused when this started proof because I had no idea why they even gave me big N. That wasn't even part of that. So yeah,
Yeah, they're going to use it for a
That's
choice.
substitution.
So what's the hypothesis for that one? It says for every and for all. We're doing a direct proof of this. We're just going to say let n be in the naturals, right? We have to take an arbitrary value, so that's our arbitrary value, let n be in the naturals. So whenever you see a for every or for all, and you're doing a direct proof, that's the first thing, you have to get an arbitrary value. Just let n be in the naturals or whatever it is. Now we have to figure out, there exists this natural number m, so we have to come up with m. And we're going to do that in a minute. We have to figure out what formula to put it. But it says there is a natural number m, so we have to figure out what m should be to make this work. And it's so that for all natural numbers m bigger than m, so for each m bigger than capital M, we want to get down to 1 over n is less than 1 over 3n. Now, if 1 over m is less than 1 over 3n, this is all I have to play with. So I'm going to try and figure out what can I do with the 3n and the m to maybe get rid of the fractions. Multiply them. So that would be 3n would be less than m, right? Now, how would I get m is bigger than 3n when all I know is m is bigger than capital M? What should we make our capital M be so that I know this is true right here? 3n. That's where it comes from. You just work backwards from where you have to go. So we started down here. We multiplied by both things so that we got rid of the fraction. And then we know that if m is bigger than capital M, we have to choose it so that this line right here is correct. And the only way that line is correct is if capital M is equal to 3n. So I'm going to fill this in here. We have, if m is greater than capital N, then we have m has to be bigger than 3n. I can put that all in one line. In fact, I could take this out right here by division. And so by division, we have our conclusion. Does that make sense? Mm-hmm. So we have to conclude those ones are a little strange. And the reason that they're getting you to think about this is when we talk about continuous functions, we talk about for every epsilon, there exists some delta, is what we call it, or limits. For every epsilon, there exists an n. And so we have to do the same thing. We have to be able to figure out what that n is. They just made, for you, a really simple calculation rather than it being longer. But we're going to get to that probably sometime in April. We'll be doing continuous functions. So let's look at another one. This one's actually kind of fun to figure out how they got to where they got on it. They said there is a real number with the property that for any two larger numbers, there is another real number that is larger than the sum of the two numbers and less than the product. Now, so I did some examples in my book, and let's think about this. Suppose that they call these like z and everything. So if z is equal to 0, choose x equal to 1/2, y equals to 1/4, and tell me what happens there. And then we're going to do the same thing. If x equals y equals to 1, and what did I have z for this one? I think I still had z equals to 0. And then if you have 1 is less than x is less than 2, and 1 is less than y is less than 2, what happens for the x plus y and the x times y? And then for the last one over here, if x is bigger than 2, y is bigger than 2, what is x plus y, and what is x times y? So look at this first one right here. What would x plus y be equal to in this case? And what is x times y? So is x plus y less than x times y? Opposite way. 3/4 is bigger than 1/8. So this one doesn't work. Because we have to have x plus y smaller than x times y. That's what they wanted in the problem. So that didn't work. Now, what happens if x times x and y are 1? What is x plus y? 1 plus 1 is 2. What's x times y?
What?
That's
You multiplying, you're working backwards. So is x plus y less than x times y?
no.
No, so that case doesn't work. Those numbers don't work. So now let's come over here, x plus y. I know that this is going to be between 2 and 4. 1 plus 1 is 2, 2 plus 2 is 4. And then multiplying, stretching. 1 times 1 is 1, and 2 times 2 is 4. So this one sort of might work, because I might be able to find something between x plus y and x times y, but they're sort of in the same range. So this one has some possibility. So maybe we choose if x is 3 halves and y is 4/3 maybe. And we'll make them both the same. What would happen if they're both the same? We have x plus y is equal to, which is 3. X times y is equal to, which is,
Or 2.12 or 2.25.
yeah, 2 3/4, 75.
Oh, really?
Isn't it? Oh, maybe. See, 9 over 4, 2.25. Yeah, you're right. So did that one work? Is the x plus y less than x times y?
Oh, wait, no.
That didn't work again.
That one didn't work again. So now let's come up here where x and y are going to be bigger than 2. X plus y has to be bigger than what?
4.
And x times y is going to be bigger than 4. So maybe we'll choose x to be equal to 3 and y to be equal to 4. What is x plus y?
7.
What's x times y? Can I find a number between 7 and 12? Yeah. So that's how they knew to choose z equals to 2. Because z is the bottom value that we're going to know is going to work. When it's bigger than 2, we can find something to work. That's how they got choose equals to 2. It was mysterious. They just said choose z equals to 2. Question?
Does that X, Y have to be, no, 2, 3, 4, 5?
No, it doesn't have to be in order. You just have to choose 2 numbers. Yeah.
Certain that there's no number above 2 that will make it not work.
We didn't say for every. We just said there exist 2 numbers. We just have to be able to find that it works.
Yeah.
So if we had wanted to spend a lot more time down here, we might have been able to find something that worked. But we don't want to spend that much time. Go to something that is easier. And the problem with this was our fractions were making things smaller. Yeah.
I was a little confused with the wording here. It seemed they say there is a real number with the property that, and then it seems like the rest is completely totally unrelated because you can just have the last part to make sense. For any 2 larger numbers, there's another real number that's larger than the sum of these 2 numbers, unless it's a product. What is the first real number? I mean, you can do with anything.
It's telling you where you can start. So we know that if you're down here between 0 and 1, it absolutely doesn't work.
Okay, so that's just a start.
That's just your starting bound.
Okay.
And we know that it definitely works when z is bigger than 2.
Okay.
And as long as we can show there exists, we don't have to show the smallest value for which it works. We just have to give a value. So z equals to 3 would work too. But the book chose 2, so we're going to use 2. Do z equals to 2.
In this section, there was a lot of like, I don't know, like, we're just going to assume this and not let you know anything about what just happened. And I'm just like,
That's why we came for the lecture. Yeah, that's because they're existence proofs. And when they're existence, they don't have to tell you how they got to that value. They just have to tell you that value worked. And it doesn't mean that no other value will work. There could be an infinite number of them that do work. They just had to pick one. Yeah.
You want them to like show you all the colors before mine.
no.
It'll be a big book. Yeah.
I was just saying, if I was teaching another section more than most, like,
Mhm.
okay,
This one.
That number.
Yeah, and they don't tell you why.
Yeah.
Yeah, that's true in this section. Okay, so we chose z equals to 2, and then that is going to be, there is a real number. Now let's exhibit the property for any two larger numbers. So we're going to let x and y be any larger real numbers. Yeah, I need to put that. X is bigger than 2 and y is bigger than 2. Instead of and, we're going to let w be the average of, write it here. W is going to be the average of x plus y and x times y over 2. We know that w is a real number, and we know that w is between x plus y and x times y. Now, what we want to know is that x plus y is smaller than x times y, and then we'll be done, right? So we have to verify that x plus y is less than x times y. How do we verify that? How did they verify that?
You do x, y less
I don't
than
know.
w less than x plus y. Oh, because w is in between. So, or no.
Well, I know it's between, but which of those two is bigger, x plus y or x
Oh.
times y?
I don't know. How did they do it?
X times one.
Yeah, but why? Remember, have I introduced you to WLOG without lots of generality? Please don't type it over and over. Just use WLOG capitals. That is a given term in mathematics. Without lots of generality, we're going to assume that y is going to be bigger than x. Okay.
I mean, the two.
If they were equal, then it would be.
Would that be good?
Yeah, it's going to work. Need to be fair. So how do we verify that? I know that x plus x, no, x plus y is where we're headed. X plus y has to be less than or equal to y plus y, right? Because x is smaller than y. But what is y plus y equal to? 2y. And 2y, I would submit to you, is less than or equal to y squared, since y is, let me put it this way. I know that y is bigger than 2. So it follows that 2y is going to be less than y times y. I'm replacing the 2 with the y. But y times y is equal to what? Y squared. Oh, I wanted an x. Sorry, I thought I was headed to a y squared. Since x is bigger than 2, it follows that 2y is less than x times y. And I don't need to go to the y squared. And so what do we have? We have x plus y is less than or equal to 2y, which is less than x times y. Notice this is a strict inequality because I know x is strictly bigger than 2. So what does that tell you? That tells you that I know that x plus y is less than w is less than x times y. Therefore, conclude.
I forgot to conclude this out loud.
Uh-oh. They will get shorter after this one, I promise.
Well, this section was just really confusing to me. So like I tried to do like most of the things, had to go to minutes. Life happens, you know.
Life happens.
Old faithful Netflix.
That is not my problem, Jason. What happened to this test, right?
Oh,
And
I-
calculus.
I believe you, I believe you.
Really?
I wish that calculus teacher of yours just wouldn't have assigned so much homework. Yeah.
No, actually, no, 3,000 and doing it out.
Oh,
Literally like 40 problems every assignment. And you know how long it
I remember
takes
those.
to find matrix?
I remember those.
Have you guys not figured out how to do matrix multiplication on scientific notebook?
Oh, I did, actually.
I
Yeah.
did.
I noticed that.
And determinants and inverses?
I noticed that.
Websites online. I mean,
I
once
was
you
gonna
do
say,
it,
yeah, it does all of it.
as long as you know how to do it.
I
you
do
should
it
be able
online now because like I know how to do that, but still takes forever.
Yes, it does. It does.
And I'm just like, why do you have 35 problems when you do 2 of the week? And I'm like, what's everybody?
Okay, did you guys understand why those forms weren't valid? Did that need explanation?
I don't remember.
That's in the very last like 2 pages.
That was where they had the numbered list and they gave an explanation for it. So
Oh, yeah.
there exists an x, p of x implies for all x, p of x. These are different statements.
Yeah.
There exists isn't the same as for all.
Yeah.
There's explanation too.
Yeah, there's explanations.
There's existing one.
Yeah, for all x, p of x or q of x doesn't mean for all x, p of x or for all x, q of x. It means that for every x, either p of x works or q of x works for that particular x.
But it doesn't
But
mean
not
that
for the whole
for
thing.
all keywords or for all
Or
keywords.
q works, which is what that would mean. And then, yeah. This one, see, this second one says for all x, p of x works, or for all x, q of x works.
Oh.
Either every number is even or every number is odd. Yeah, that's a big difference. Then for all x, p of x implies for all x, q of x. That's not the same thing as for all x, p of x implies q of x, because over here it says if p of x holds for every x, then you know q of x holds for every x. But here it says for all x, if p of x is true, then q of x is true. That's not the same thing. Actually, the left-hand side one is a stronger statement than the right-hand side one. And then the last one, for all y, there exists an x so that p of x, y is true. There exists an x so that for all y, p of x, y is true. That's not the same thing. This says that for every y you choose, you can find the x that matches with that y. The other one is saying there exists an x so that every y you choose will work. And that's not the same thing. Yeah. Yeah. That's exactly right. And then they gave us this example, which we can laugh at humorously now, but we struggled with it in our day too. X plus y, yeah, you tutoring?
Oh, yeah, me
TA,
too.
yeah.
Me too.
They really want that.
They wanted to.
It's so bad. But it doesn't work.
Also
You have
the
to
square
FOIL
root
it.
of x squared plus y squared.
Yeah,
Take it
it's
out,
x
take it
plus
to
y.
school.
Yep. No, it doesn't work. No, it isn't. Not at all.
Only.
If only life would be simpler, well, and more complicated at the same time.
Yeah,
Yeah.
I was gonna say, it's a
One
lot
of us.
faster to do it the first time.
But x plus y squared equals x squared plus y squared.
Is that everything goes a lot? or not?
Yeah. Then all your math teachers have lied at you for the first
Oh, yeah.
12 years or 13 years or 14 years. Yeah.
Then just
So we changed everything.
Yeah. Okay, so the last one, it says there is no odd integer that can be expressed in the form 4j minus 1 and in the form 4k plus 1. And they did this one by contradiction. So you assume that there exists an odd integer, n equals to 4j minus 1, and n equals to 4k plus 1 for some integers j and k. Then what do they do? What you're trying to do is arrive at a contradiction. These are the hardest ones because we don't always know what the contradiction should be.
Or you want, or you want to just say it's equal.
You want to be
Well,
all
they're equal, so. that's
Yeah,
equal.
they're equal, and that's exactly where we're headed. So we're going to say 4j minus 1 is equal to 4k plus 1. And then what should we do? Combine like terms. So we're going to have 4j minus 4k, or minus 2 equals 0. It doesn't matter. So then what should we do? Factor out of 2. And then we have 2j minus 2k minus 1 equals to 0, where 2j minus 2k minus 1 equals to r is in the integers. What does that tell you?
That your original statement is even, so if I kind of.
Wait, I think we missed a step here.
No, no,
Equals to
because.
n.
What if we set this equal because it would have to say
Yeah. We don't want to.
minus 1 or
We
equal
want-
to 1.
Equals to
We
n.
don't want it to be equal to 0.
One side is even and the other side is odd.
Oh,
Yeah, we want it equal to 2.
Therefore, the statement is false. Or
Yep.
the original. Shouldn't keep the J's at the same time, the side is wrong.
No, because
what you.
we're going to divide by 1, or divide by 2.
If you factor out a 2, you can assume that j minus k is equal to some random number r, and therefore 2r is equal to 1, and 2r is even and 1 is not. Therefore, it's not good. That makes sense?
Well, I think j minus k has to be equal to half the number that they were integer.
No. It's just saying that an even number equals an odd number. Rather than trying to argue that j minus k wouldn't be an integer.
Okay.
I mean, your argument is correct, but it takes about 10 more lines to get there, which is why I'm keeping us away from there. We have to talk about division and stuff, and that's a whole half of an abstract algebra course.
So, but is it 2 integers? The add or subtract?
Yeah.
If we're gonna say that, we need to keep the j's and k's separate, so we're actually having the definition of even and odd on the opposite side.
Well, they are. It's right here. You have 2r equals to 1.
Because when you have 2 integers, when you add or subtract integers, it's still an integer, right?
Yeah.
So j minus k
It's
will
still an
always
integer.
be an integer.
And this states that 2r,
Oh, I guess you need to know because one side's even, the other side's odd.
Could I say this? Feel shorter. Because this is the definition of even, that's the definition of odd.
And if,
Because you had
if they
Oh,
equal, they do not equal each other.
one, move it over, and you have even. and
yeah,
odd.
you could do that. I see what you're going with that.
So now there's a contradiction.
Yeah. Yeah, you can go that direction too. And conclude.
So why do they have these like trapezoidal desks instead of like this normal?
This is a math department